let me now give you two very important relations. But before that, one more example for the pseudo first order reactions. So it is hydrolysis of ester in the presence of acid. Okay. Now, look at this. So this is ethyl acetate. Water is again taken in large excess in the presence of acid catalyst. It undergoes hydrolysis to form acetic acid. Okay, you can just cut it here. Acetic acid, and along with that, you get ethyl alcohol. So ester on hydrolysis forms acid and alcohol. Okay, now see, for this reaction, the rate expression can be written as K into concentration of ester to the power 1 into concentration of water to the power 0. So order with respect to ester is 1, whereas that with respect to water is 0. Rate is independent of concentration of water. As it is taken in large excess, right? So this again is a pseudo first order reaction. Okay. Now let us derive two very important relations. Taking the expression for first order rate constant expression 2.303 by T into log, say, A by A minus X. Now, let me write this expression in some other way like this. Now, you know, K1, of course, is a constant. Remember, it depends only on temperature. Rate constant of first order. Okay. Now, removing the constants, we can write a proportionality. T is proportional to log A by A minus X. Okay. Now, from this, we can write this. T1 by T2 is equal to log A by A minus X in the first case, by log a by a minus x in the second case. We come across so many problems on this particular relation. Like they'll be giving you a question this way: 90% of a first order reaction is completed in say 30 minutes. When will 99.9% complete? So in that case, your A will be 100 and the reacted will be 90 in the first case, and you are given the time. In the second case, again, A will be 100, but X will be 99.9 because that is the reaction which has already been completed. And you have to calculate this T2. So this way, we can take any number of examples. So very important relation. Now, the second one, that is, in fact, applicable in case of radioactive decays. It can be given as W is equal to W naught by 2 power n, where this W is the amount left. W naught is the initial amount. N is the number of half-lives. Now this N can be given as T by T half, where this T is the total time and this T half is the half-life. Okay. So this also is a very important relation. Yes. Let us now go for second order reaction. What is a second order reaction? See, if the rate of a reaction depends on two concentration terms. It is known as second order reaction. Concentration depends on, rate of reaction depends on two concentration terms. Or you can say that the rate of reaction depends on second power of a concentration term, or on first power of two concentration terms. So that way it can be given. Or else we can also say that if the rate of a reaction is determined by the change of two concentration terms. It is known as second order reaction. Okay. Now, let us consider a reaction 2A gives rise to products. We can even consider the same as A plus B gives rise to products. You can also say this as A plus B plus C in large excess gives rise to products. Because C is taken in large excess, that will not be affecting the rate. Okay, that way also can be taken. Now let us write this in a different way. Instead of going for minus dA by dt, let me give you the second and third orders in this format, dx by dt. Now whatever is going to react from now on, x is the one that is going to react from now on. It depends on the amount of A left. Okay, that is A minus x. At that particular instance to the power 2. Or else it can be written as minus dA by dt is directly proportional to concentration of A square. But for second and third order reactions, would actually like to give it this way, just for difference. Now this can be written as dx by dt is equal to k2 into A minus x whole square, dx by A minus x whole square is equal to k2 into dt. Now this on integration gives us the final expression. See, on integration we get the expression for rate constant of second order reaction 1 by T into x by A of A minus x, or else simply 1 by AT into x by A minus x. Okay, so that is the expression for the second order rate constant. In fact, not that often we get the second and third order reactions because we have only up to the first order reactions, but because it is the same as what is in case of zeroth and first, I'm taking all these. Now, in this case, it can be given as dx by dt is proportional to A minus x to the power 1 into B minus x to the power 1, because you have taken two different reactants. Okay, so this can be written as dx by dt is equal to k2 into A minus x into B minus x, dx by A minus x into B minus x is equal to k2 into dt. Then on integration, we get the final expression for k2. Just check this out. Think you are all very much familiar with the integration thing. So 2.303 by T of A minus B into log b of a minus x by a of b minus x. Okay, so that is the expression for the second order rate constant when two different reactants are taken, in case of which the rate depends on the first power of their concentrations. Okay, now the expression for half-life, taking the second order rate constant expression, K2 is equal to, okay, let me do this way. When T is equal to T half, X, that is the amount reacted, will be half of what is taken, A by 2. Now substituting this in the expression for K2, K2 is equal to 1 by T, will now become T half. 1 by T into X. X is A by 2 by A of A minus X. Okay. So K2 can be given as, look at this. Now this is A by 2 and this also is A by 2. This can be written as 1 by A into T half. Now look at this. T half is equal to 1 by A into K2. See this. T half is inversely proportional to A. Okay. So this is a very important thing. In case of zeroth order, it was directly proportional to initial concentration. First order, independent of initial concentration. Now, in case of the second order, it is inversely proportional to initial concentration of the reactant. Okay. Let me give you some examples for second order. H2 plus I2 gives rise to 2HI. In this case, rate depends on the first power of both the concentration terms. Then look at this. Quite interesting. In this case, rate depends only on the first power of the concentration of NO and on the first power of the concentration of F2. Look at the stoichiometric coefficient of NO and look at the power. Okay, so powers have nothing to do with the stoichiometric coefficients. Then the very important hydrolysis of ester in the presence of base. Okay, so these are the examples for the second order reactions. Now it's the third order reaction. What is third order? If the rate of a reaction depends on three concentration terms, it is called third order reaction. We can also say that the rate of reaction depends on the third power of a concentration term or second power of one concentration term and first power of another concentration term, or first power of three concentration terms. This way, we can give the rate expression or rate equation in different ways. Okay. If the rate of reaction is determined by the change of three concentration terms, it is a third order reaction. Okay. Let us consider this way. 3A gives rise to products, of course. Can also be taken as 2A plus B gives rise to products. A plus 2B gives rise to products. A plus B plus C gives rise to products. Or even A plus B plus C plus D in large excess gives rise to products. That way also is okay. Now, like what we have taken in case of second order, let me take dx by dt. I mean, the amount of A going to react from now on, from this instance, is directly proportional to the amount of A left at that instance. Okay. Because rate changes every instance. Every time we need to add this word at that instance. Okay. Now, this can be written as dx by, okay, dt is equal to k3 into a minus x whole cube. Then dx by a minus x whole cube is equal to k3 into dt. Okay. Now this on integration gives the final expression for third order rate constant. Some similarity with that of the second order. 1 by 2t into x of 2a minus x by a square into a minus x whole square. So this is the expression for third order. We will of course go for this rarely, but still. Okay. Now the expression for half-life. As usual, when t is equal to t half, amount reacted is taken by 2 or initial by 2. Now substituting this in the expression for third order rate constant, K3 is equal to 1 by 2 into T, that will now become T half, into X, nothing but A by 2, of 2A minus X. X of 2A minus X by A square into A minus X whole square. Okay. So now simplify this. We get K3 is equal to 1 by 2t half into this, of course, has to be simplified a by 2. Let me write the final expression as 3 by a square. Okay. Now from this, the expression for t half can be written as 1 by 2 into K3 into 3 by a square. Now from this, it can be written as t half is inversely proportional to a square. I mean, half-life is inversely proportional to square of initial concentration. Okay. Let us take some examples. Two NO plus O2 gives rise to 2NO2. 2NO plus Cl2 gives rise to 2NOCl. Okay. So this is about third order reaction. Let me finally give you the expressions for rate constant of nth order and of course the expression for half-life of nth order. In general, nth order reaction can be given as Na gives rise to products, then dx by dt is proportional to a minus x to the power n. So dx by dt is equal to kn of a power x minus, a power x to the power n. So then this can be written as dx by a minus x to the power n is equal to kn into dt. Now the final expression for kn can be given as 1 by t of n minus 1 into 1 by a minus x to the power n minus 1 minus 1 by a power n minus 1. So this is the expression for nth order rate constant. T of n minus 1. A minus x to the power n minus 1, then a to the power n minus 1. So very simple. Now the expression for half-life of nth order. As usual, when t is equal to t half, amount reacted x will be initial by 2, a by 2. Now substituting that in expression for kn, t of n minus 1. Now let us write it as t half of n minus 1. Okay, 1 by a minus x of n minus 1. X is now a by 2 by 1 by a power n minus 1. Okay. So this kn can be written as, let us write one more expression. T half into n minus 1 by this is of course a by 2 to the power n minus 1 minus 1 by a power n minus 1. Then let me write the final expression for t half. 1 by kn of n minus 1 into 1 by a power n minus 1 into 2 power n minus 1 goes into numerator. 2 power n minus 1 minus 1. Okay, so this is the expression for t half of nth order reaction. Check this out.